Hello and welcome to the Mechanical Engineering Research Seminar. So we're starting today and we'll do this every Thursday at 2 p.m. For the remaining of the semester. So our first speaker today is Dr. Weibing Xing, who's new to our department. He'll talk about his battery and energy storage research. So he comes up to us from industry. He was previously in Littleton, Colorado at ADA Technologies, and he'll introduce himself and his research, and hopefully those of us that are in person can hear, and those of us that are online, or those of us that are hearing this recorded can all connect. So welcome.
Thank you, Mike. So I should point out this camera, right? Mike?
You're fine.
So
it's this camera.
Yeah.
Yeah.
So good afternoon, and I'm going to just talk about the screen. Can this see the screen as well? Or?
Yes.
I'm talking about a little bit, the lithium-sulfur battery research, and then why it is beyond the lithium-ion. So hopefully I can move this around. Okay. So for those who are not quite familiar with the battery, I'm just give this one page battery 101. Okay. So for the battery to work, you'll need to have an anode, which is the negative electrode, and then you need to have a cathode, and then which is the positive electrode. And then you have the electrolyte in between. And so those are the three major components. And then this electrodes need to be separated, otherwise it will be short. You have a short circuit. So basically we use a separator. So those four components are essential for the battery. And then after that, in order for the battery to work, for example, to lit the light, then you need to have an electron to flow. And the electrons flow from outside circuit to do the work. And then to have a complete circuit, you need to have the electricity flow inside as well. So what it's doing is that the electrons flow this way, and then the positive ions inside the battery flows that way. So it won't make sense. So the electric circuit is complete this way. So so that's all about the battery 101, and then let's move to the next one. So I think most of us heard the lithium-ion batteries, and because it's everyday life. So there's no exception for lithium-ion battery. You have to have anode, you have to have the cathode, and the electrolyte. So in this case, the anode is the graphite. Basically, it's a carbon. So it's a layered structure. And then the cathode is the metal oxide. So one very popular one, probably this one actually is in everybody's cell phone, laptop, is the lithium cobalt oxide. So this one was discovered by John Goodenough, and who was the one of the recipients of the last year's Nobel Prize. So this is one of the materials. And so the lithium-ion actually, when you charge goes to the anode, and then when you discharge goes back to the cathode, and then so it moves back and forth. So that's why it's called the lithium-ion. So what is moving is lithium-ion. So the battery has been commercialized for about 30 years, in the earliest 1990s by Sony. So what is good about lithium-ion? So advantage is one of the advantages is represented by this Ragone plot. So what it is, we plot the gravimetric with energy density. In the battery world, we like to call it the specific energy in terms of watt-hour per kilogram, and then this energy density, the typical volumetric energy density. So the watt-hour unit is basically, watt times hour times time is unit of energy, right? It's joule. So higher watt-hour per kilogram, meaning that stack smaller amount of material for the same amount of energy. So it's lighter, right? So it goes lighter. So then if you look at the other way, so higher watt-hour per liter, so that means that you can, have a smaller volume for the same amount of energy. So lighter and smaller. So lithium-ion, comparatively speaking, has more advantage over the other, battery chemistries. So that's, the advantage. So due to that advantage, so it's been widely, applied to, all the applications, so everyone has the cell phone, laptop, the chances are, almost like 100%, you have lithium-ion in your cell phone and laptop. And then the other applications, power tools, EVs nowadays, are all made from the, powered by the lithium-ion. And then other applications, medical, space, defense. So the due to the advancement of the let's see. So,
Sorry.
yeah, due to the advancement of the science and technology, so the the lithium-ion finally got recognized by the Nobel Prize, and then it went to the chemistry last year for the lithium-ion batteries. So and Jiang and then Stan are frequent attendees of the battery conferences we meet all the time. Actually, I talked to two of them, and then I actually in person congratulate Stan. And then just one little story. At one conference, I met John, and then we actually happened to sit in the bus to the conference from a hotel. And then he was like so down to earth, and then he's very humble, and then we talk about science, everything else. So that's kind of my experience with those people. Then after 30 years, people ask what's next, right? So, and then for this, schematic, it just shows, the direction for higher energy, and then safer and then cheaper chemistries, like, cathode here, anode here, electrolyte in the middle. So we are here today, and towards the future, you can see sulfur here, sulfur, lithium, and then that's lithium sulfur. And then the other chemistry is called the lithium-ion and lithium-air. So those two chemistries are, sort of like beyond lithium-ion chemistry. So then when you analyze them, the lithium-ion air is kind of a little longer term because, more challenge than the sulfur. And the sulfur is kind of mid to long term. So, which is considered, the most promising beyond lithium-ion candidate. So that's why we jump into lithium sulfur. Obviously, it should have an advantage. Obviously the energy is one of them. So the reaction goes like this. It's not that complicated. It's very simple. It's sulfur plus lithium plus some electrons. So it goes to lithium sulfide. So back and forth. Then in the battery world, we use the specific capacity to measure the electric charge per mass. So this is we use. So here the ampere hour, basically ampere times time basically becomes the electric charge, right? So it's the coulombs, and then per mass. So for the sulfur is a cathode in this case, and then has a high specific capacity of almost like 1700. So which is 10 times about the lithium-ion, lithium cobalt oxide cathode. And so for the anode side, is the lithium anode has a high specific capacity of almost 4,000, and then which is 10 times than the lithium-ion anode. So if you combine this together, and then you get the lithium sulfur specific energy about 2,500. So which is about 7 times the lithium-ion. So which is significant, right? So that's why this is attractive. So some other advantage, like sulfur is naturally abundant and low cost, and then the chemistry is environmentally friendly, and then so intense R&D has been going on for the last recent years for this chemistry. Now we start looking at this chart. So this chart is when you plot the cell voltage against the specific capacity, and then so what we are looking at is that this is a discharge curve, and then discharge meaning that for your cell phone you are charge it up during the overnight. The first thing you use it, that's where it is. We start the battery here is fresh. So for the sulfur chemistry, when you start it, so the sulfur combines with lithium because lithium 2s8. So this is what we call it polysulfide. And you further use your cell phone, and it means that you further discharge the cell. So the curve follows like a little bit plateau here and a long plateau here, and then it converts to lithium 2s6. So sulfur is further reduced, right? So then when you first discharge, first using your cell phone, and then it becomes like further reduced to S4, and then S2, and then lithium sulfide is the final product. You cannot further reduce that, right? So this is the time when your cell phone needs to be recharged. So this is the whole discharge process, and then after that you charge the battery, you charge it back to sulfur. So far so good. What's the problem? So the problem is that those polysulfide dissolve into the electrolyte, so especially for the higher water, and so when that happens, so the polysulfide ion diffuse into the negative lithium anode. So why that is bad? The reason it's bad is that it starts to you lost the sulfur in the first place, right? So it shouldn't move. It moved to the other side, and then it corrodes the lithium metal, which is not a good thing. And then it creates self-discharge. This is another term, battery term. That self-discharge means that when you not even use the battery, and then the battery life becomes like reduced by itself. So that's called self-discharge, which is not very good. And on top of that is that there's more challenges. So this is a phenomenon called shuttle mechanism. So what it is that at the higher order polysulfide diffuses to the negative electrode and then react with the lithium ion to form the low order polysulfide. And then they won't stay there, and then they actually shuttle back to the positive electrode. So imagine you charge the cell, right? When you charge the cell, you want to oxidize the sulfide back to its original sulfur, and then you can't do that because once you reduce this higher order to lower order, you have a more higher order due to the shuttle. So you're kind of back and forth. You're just doing nothing about your charge. You don't charge it. You can't charge it. So that's kind of very, very low charge efficiency. So that's called shuttle phenomenon, so which you don't want. So that leads to capacity. And then another thing is that sulfur is not a very good conductor. So you can see here very, very low conductivity, and also the lower order, the final product are insulating by itself. So so that leads to let's say very poor power capability. So why power capability is important? For example, if you charge your cell phone overnight, that's normal. But sometimes you can turn the mode to like fast charge, right? So you need the cell to work in a couple of hours. You turn into another mode, so you charge it for 2 hours, right? So that actually speaks about the power. So the faster you charge, the higher the power. So you need the power capability for the battery. So if you lose that, then it's not very useful, right? So another challenge is that, metallic lithium anode is by itself, it has a safety concern because it has tendency to kind of grow like a dendritic, like needle-like. That's not a good thing because you can penetrate through and make short circuit, right? So when I was at ADA Technologies, and we carry out the lithium-sulfur research under the Army SBIR phase 1 and phase 2. So by the time the Army's program goal is that okay, so the specific energy for the cell, we're not talking about the material. So previously I showed the large number, so that's for the material. So here the cell, with everything put together, the whole cell need to be like more than 300 watt-hour per kilogram. So and compared to speaking, lithium-ion is about 250, so it's about 20%. So and then the Army also asked for cycle life more than 100 cycles. So again, in a battery field, when you talk about the cycle life, you're always referring to 80% retention. Okay, so let's say you have 1,000 cycles life. That means that you have 80% at the end of the 1,000 cycles. Okay, so still to achieve the Army's performance goal. So what we come up with is that we took a holistic approach to achieve synergistic benefit from all the cell components, just not one. So, and not include the cathode, sulfur cathode. So one of the approaches is we coat from the atomic layer or molecular layer deposition, the LD and MD, for the material to the sulfur. So here is the coated material. You can see the sulfur powder is in there. And so another approach is just optimize the formulation. And so one of the tools we use is ball mill to achieve that purpose. And then the other one is the lithium anode, where it's sort of the material engineering. So we LD coat the lithium. So this is actually coated. So you see it's not silver or shiny. It's kind of this color. So why we do that? The purpose is that we try to encapsulate the polysulfide with the coating and impede polysulfide migration, so we don't have to happen, and enhance the ionic and electronic conductivity, and then last one is to prevent lithium dendrite from formation. So those are the intended benefit. And then another approach we use is the separator. So we modify the separator with a conductive medium. And here on the left is the pristine, the normal separator. And then it's like that, and it's polymer. And then the coated, we call it functional separator, is like coated. So why we do that? And then the reason is we try to accommodate the polysulfide from this functional separator, and also we help reactivate accumulated polysulfide. Remember, the end product of the polysulfide is not very conductive, so those are the purpose. And then the third approach we use is from the electrolyte. So here we like to kind of formulate the electrolyte so that we add some functional additives. So this is give some kind of example. One is some lithium nitrate and some polysulfide, and then here and here. So the purpose for that is to form some passivation films on the lithium anode, and then so that it protect, to provide a protection layer to minimize the electrolyte decomposition and to prevent dendrite growth, and then to achieve the high cooling efficiency. This is another battery term, and so let me explain a little bit. So the cooling efficiency is defined as CE, we call it. It's the measure of charge efficiency. So it's equal to the ratio of discharge capacity and then divided by the charge capacity. So So desirably, we would like to have the cooling efficiency as close to 100% as possible, and so that's that. So due to the limited time, and I'll just like pick up some of the material engineering examples. One example is the sulfur electrode formulation optimization. So I just listed two of the the formulations. S1, S2. So here we have the sulfur material 75%. So we would like to have this sulfur material as high percentage as possible. For obvious reason, you don't want some dead weight or electrode for the sake of energy, right? And because of the poor conductive nature, we want to add carbon black. We want to add some graphite, so to increase conductivity. And in this S2, we add a little bit CNT, which is the carbon nanotube. So again, for the purpose of increased conductivity. And then here we show some kind of finished sulfur electrode. So this binder is helping for adhesion to the carbon to the substrate. So this is the finish, and then electrode. And then another approach is I want to give some example the electrolyte formulation work. So here I just chose like two examples. One is E1 and then E2. So you can see that for lithium, the electrolyte you have like lithium salt, LiTF6, the formulations here, and then dissolve in the DME and the DOE here, and then we add a little bit the additive lithium nitrate, and then this E1, and then you can see that for E2 we add a little bit more polysulfide here for the E2. And then you can see once you do that, then the electrolyte turns a little bit like brownish. And then so that's still usable. I mean, sometimes when it turns to brown, you say, well, it's bad. You know, so this is actually normal electrolyte in this case. All right, so once we have all the cell component, we like put everything together, right? Anode, cathode, we use the baseline, normal separator as our control, and then we use a functional separator for the advanced cell, and then all kind of various electrolytes. So what we do is in the lab, for a quick, efficient way of evaluating, we don't want to use like a real cell, right? So that's kind of costly and not use a lot of materials. What we do is we use coin cells. Okay, just like a button cell, you have watch, button cells. You sometimes see that, and then it's quicker, it's very efficient, and then it's easy to make. And so once you do the prepare the cut, the coin cells, you put into the cycler. You put together and then connect it to the wire, and then this wire goes to the battery cycler, and then you evaluate the performance. So that's how we evaluate the sulfur battery in a battery in a laboratory scale. And so again, due to the limited time, we just don't go too many examples. I just want to show the impact on the lithium sulfur cell performance from the three sort of like approach. One is the functional separator, the control versus advanced, and then another one is the sulfur cathode formulation. How that impact. So S1 versus S2, and then the third one is electrolyte formulation, E1 versus E2. So first one is the separator, right? The functional separator, how that impact. So again, we have this, the plot of cell voltage versus specific capacity or voltage profile. Okay, so we can see that for the advanced cell, it shows this nice two sort of plateau here and here. So the lower plateau is the one that contributes the most of the capacity, so it's long. And so we'll measure at the end, discharge, what is the specific capacity. So for this advanced cell, it delivered almost like 80%, more than 80% of the theoretical specific capacity. So, and which is actually, considered very good, given the sulfur chemistry. And, if you look at the control cell, without this functional separator, those plateaus are shorter, and then which leading to the smaller specific capacity, only like 50%. So that's a good example is that if you don't do the material engineering and then optimize the cell component, this is what you get. You get very far from realization of the true potential of the sulfur, and so that's the importance of that. And then one thing I like to mention that in the battery field, we use the C rate a lot. So C rate just very simply meaning that when you say C over 20, meaning that you'll complete discharge or charge the battery in this 20 hours, X hours, C over X. So whatever that X number is. And then once we do this, voltage profile, we like to see how the battery performance versus cycle. So when I say cycle, meaning that you're actually doing the cycle every day. Basically, when you use the cell phone, you kind of discharge the cell. And then at the night, let's say the cell is completely discharged, you plug it in to charge it, and then in the morning, you total charge 100%. Then that's considered one cycle. So one charge, one discharge, that's one cycle. So we are doing this in a controlled way. So, many cycles. And so we are looking how our capacity is plotted against the cycle number, right? So you can see that, for the advanced cell, it has, almost twice as the capacity delivered and then throughout the cycle. The second thing that we notice is it's initially it's a little bit fading, but it becomes stabilized. So and then it lasts like more than 80% of the capacity after 100 cycles. So so this is why this is important. The reason being that when you use the cell phone, you notice that over time your talk time is shorter and shorter and shorter. The reason being exactly is this. It's because when you use it, when you cycle it, your capacity is fading. It's inevitable, but you want to keep it as slower as possible. So that's kind of what happened here. And then here it just shows the importance of the functional separator, for the good rate capability, because we discharge it. Remember when we do the plot for the discharge curve, we did it C over 20. Here we did C over 2. The reason being that A, it is faster, so we get more data. B, the C over 2 means 2 hours. That it is more close to the practical usage, right? So that's reflected by the rate capability. So and so those the function just by changing the functional separator, you'll have those advantages. So another example I like to show is that how the impact of the sulfur electrode formulation on the performance. So remember we have S1, S2, S2 have CNT in it, and you notice that the discharge curve has a little bit higher profile than the S1, and also it's a little bit more capacity. So although this is not much by 50 millivolt, but then if you combine this two together, it just leads to the higher specific energy. The specific energy equals specific capacity times voltage. So when this all adds up, so it has an advantage in terms of performance. And when we look at the cycle life again, and we compare the S1, S2, so you can see that the S2 cell has almost like 20% more higher specific capacity, and then throughout the cycle life. So and that kind of tell us the rate is better. It delivers more, capacity just for the, for using different cathode formulation, and so that's indicate what we show here is that it's important of the even just cathode formulation to achieve the good grade and the cycle life. So another figure of merit we look at is this cooling efficiency. Okay, so when we plot the cooling efficiency versus cycle number, and remember we like to have as close to 100% as possible. And for this S2 cell, you can see that it shows like almost like 99%, which is pretty close. For battery, that is a good number. So and the second thing is that it's pretty stable. And then so that shows like stability. And so you can see that it is a little bit higher than the S1. So let's say it's 2%, but this apparent small CE difference will lead to long-term stability, because if you cycle like longer, more cycle, that make a difference, because the here S2 is, S1 is less efficient, it consumes more, cell components. Final example is that we show that the impact of the electrolyte formulation on the cell performance. So here, remember we have two examples. One is E1 and another E2, and so E2 has a polysulfide active in it. So when we compare them side by side, and we see that for this E2 cell, you have further extended, this, plateau, this is high voltage plateau, and then low voltage plateau is all longer than the SE1 cell. So if you look at, at the end of this chart, you look at, the capacity delivered, it is actually pretty close to the theoretical. That's actually very amazing. For sulfur chemistry, the literature work, if you search it, basically not many, results just showing, close to the theoretical value. So they are kind of, in 1,000 or 1,200 in those range. So this is actually pretty amazing that, just by, electrolyte work, we can achieve this type of, advantage. Obviously, this type of performance is just a combined benefit, because not only the E2 polysulfide active, but also the optimized the cathode and also the functional separator also contribute as the to sort of as this combined benefit to lead to this resultant lithium-sulfur cell performance advantage. So when we calculate, based on this performance, and then we can calculate, what is the specific energy. Remember, the Army goal is for specific energy more than 300, right? So this cell performance actually translates into like, almost like 400 watt-hour per kilogram. At the cell level, this is the real cell level, which is actually 60% of increase over the lithium-ion. So another reason for the, why the lithium-sulfur is so interesting. So because of the huge energy density gain. So that drives the research into this chemistry. So, and then we are kind of curious that, for all the button cells or counting cells, they are small, they are laboratory scale, right? So they are not practical. So then what we're asking is that, we did some preliminary, so what happens if we kind of scale it up to a pouch, we call it a pouch cell, just like, this kind of type of cell. And so what happens is that, when we scale it up, so this is the cell, and then when we discharge it, and then it shows that, again, two characteristics, voltage profile, plateaus, and then in the end, it delivers, a good capacity, 1,100 milliamp per gram. So it's not as good as the Coin, but it's a good number. It's the first, first initial try. So that indicates that, there's a, promising way to kind of, make this into a practical chemistry for, applications, right? So that's the purpose. So so we showed that our study demonstrated that the material engineering of the active and then inactive material component is critical to realize sulfur batteries potentials, of the high specific energy while retaining the very long cycle life. So we also, our study suggests that to overcome this technical barrier for sulfur, and then we do need a holistic approach that is to provide synergistic performance benefit to the resultant advanced lithium-sulfur battery cells. So that's kind of our conclusion from this study. And then just the last slide just shows future research. So we would like to kind of continue the lithium-sulfur battery research at school mines, and then we will work with the US IU CRC Center. We propose solid state lithium-sulfur batteries. So that's another frontier for safer, higher energy, more better performance. And then we work with government sponsored programs and also industry collaborations. And we'll welcome all type of collaboration from campus and campus or hot campus. So so that's basically my presentation. So last one is thank you for your attention.
So we have about 10 minutes. There's 11 people online and a few people here. So we'll see if anything pops up. And you might need to repeat his question.
So a couple of questions. One is, you looked at different, I think it's anode chemistries with the sulfur, with the polysulfides mixed in, or with carbon nanotubes mixed in?
Yeah.
Right, the cathode. Yeah, the cathode. So how did you determine what volume fraction, whatever, of CNTs you wanted to explore? And the same thing with when you added the polysulfides.
Yes, a good question. So when you add this active, so you want to kind of take advantage of carbon nanotube. For example, in terms of carbon nanotube, is it's longitudinal, one-dimensional, and it provides a good conductive pathway, but also it is expensive. So you try to minimize that, and also we found out that adding more doesn't mean that you have the same proportionally increase of the conductivity or performance. So there's some kind of amount that it's just enough. So that's the reason for the amount of carbon nanotube. And then the other component is as I said, the sulfur is active material. So basically, in theory, for the lithium-ion battery, so basically the lithium-ion battery, that's the battery in the cell form. Actually, this amount is about 90%, more than 90%. And typically, it's like sometimes even like 92%. The reason being, the cathode material is not very insulated. Its itself is very conductive. So you don't need as much of the conductive medium to help increase the conductivity. So, and that's kind of one of the challenges for sulfur. Some people put like even like 50% of sulfur. The rest is all conductive medium. So the drawback is that you have so much dead weight, let's say, and then you don't really realize your advantage because once you put so much dead weight, so your battery is like almost equivalent to the lithium ion almost. So that's the reason when you balance this off, you want to minimize actually all the actives. You want to maximize this sulfur active material, and then so that's kind of the design guideline.
Thank you.
So certainly this is research at the benchtop. You have you've previously gotten SBIR, the Army is interested. How close is this technology to being, on the market in my cell phone in my pocket?
Yes, that's a very good question. So
Could you repeat the question just so we
yes,
understand?
okay, yeah. The question is that, we did, this, SBR research under Army. How close is the lithium-sulfur battery, close to, the real, product, and then to, for cell phones and laptops. So that's a very good question. So I would say the sulfur chemistry is still in the mid to long term. The reason being that, we still kind of, work out, all the bugs. For example, for the battery performance we showed today, so sometimes you show, initial very high, capacity, but then, you have to overcome, what about, the cycle life? Can you maintain extremely high capacity, over the cycle life? That's number one. Number two is, how do you balance the cell components? For example, when we do the laboratory, we put, a lot of, extra sort of, like electrolyte and then, lithium anode. So that just to study, the cathode. But then for the real application, you want to minimize the lithium as well, and then the electrolyte. So when you do that in a more realistic way, then what happens is that the performance actually becomes like, deteriorating faster than you actually, optimize the, all the, we'll use a lot of extra material. So those are the practical, issues that we need to overcome. So actually, we also have a NASA sort of phase 1, and the phase 2 actually is coming. But obviously, I may actually, helping on that, from the contract to work with the ADA technologies, so that that project is actually for the power source used in the moon surface. So for moon exploration. So NASA actually, founded out phase 1, and then we made a good progress, and then they found phase 2. So so that final goal is to launch a lithium-sulfur battery to the moon and then use on the moon surface. So how far away from there? I think for the first generation, probably is a couple of years. I would say optimistically, because you may not have the best performance at that point, and then you have some kind of short term. That's why, like for example, Army, they don't ask for thousands of cycles. They only ask for like 100 cycles. That's good for my soldier, right? My soldier goes out, and then we use it for a couple of times, and then we come back. So for those type of applications, don't require a very, very long cycle life. So lithium-sulfur becomes a more realistic application, like for EV, for other laptop. So we need a more robust battery chemistry to kind of have longer cycle life.
Hi, this is Prasoon here. Can you hear me?
Yeah.
Yeah, my question was because of having sulfur, is it any toxicity, any toxic kind of effect expected to have because of sulfur being present? Any chemicals being formed, any toxic chemicals being formed as a result of the reaction, anything, any kind of side effects?
Yeah, okay, so I got your question. The question is any like a toxic effect from the lithium-sulfur chemistry and the battery? So I think the answer is generally, I think the answer is mostly no. The reason being that, if you look at the electrolyte used, I mean, sulfur itself is benign, right? So it's not toxic, sulfur. And I know you're probably thinking about hydrogen sulfur, right? So that's very toxic. But then we are not producing that at all, because if you look at electrolyte, and then if you look at the reaction pathway, so basically what you have is you produce this curve. the theoretical curve here. So basically what you produce is lithium sulfur, and so that's not toxic. And then that's not very toxic. And also, the real life experience of the lab is we actually, initially when we taught this one, we had no experience, right? So we're kind of concerned whether there's, some kind of, smell, some kind of toxic. But then when we build the cell, when we open the cell, really there's not much smell at all. So I would say, the chemistry, but it's not very toxic, from the chemistry point of view, even from the electrolyte point of view, it is not very toxic because we just use the some kind of lithium salt, and it is moderate. I mean, you don't want to use that one, but the DME that's ether based, and then so it's not considered a very toxic chemistry. So I would say overall, it is benign.
Okay, thank you.
Any more questions?
Hey, Weibing, this is Chula. I have a questions. So when you go through this cycle of the lithium, can you hear me?
Yes, I can hear you.
So when you go through this lithium cycle, right, you start from the lithium-sulfur 8 and then you ended up lithium-2 sulfur, right? When you have this multiple transition essentially, do you develop some kind of how does that transformation goes through? Do you have some kind of crystal structure change or volume change? Does it create some kind of stress in your battery overall cell? Or can you comment something on that?
Yeah, okay. I think the polysulfur intermediate, we call it, it's just inevitable. So ideally, you would like to have sulfur 8, let's see, sulfur 8 directly go to the final product, right? So, and then unfortunately, the sulfur and the lithium, it does form this intermediate. So I think the crystal structure, and I mean this is polysulfide. This is all lithium 2 and then SA642. So they are smaller, but you can see just from the drawing, I don't know, they are becoming like smaller and smaller. But so that's kind of in terms of first question. So they are very dissolvable into the electrolyte, and then they can become an ion. So like for this sulfur ion plus the lithium ion, right? Because lithium becomes the cation, and the sulfur becomes iodine, right? So become an ionic in an electrolyte. So they are not even like a crystal, right? So but then when you further discharge it, so let's say towards the end you have lithium 2s, right? So these are basically actually is a solid, right? So those are the solid. So and then the intermediate is not. The intermediate actually in the sulfur content, they are actually ionic species. They are actually swimming around in the electrolyte. So that's one of the challenges that because they are so mobile, that actually creates all kinds of problems we describe. So our key is how do we kind of contain those kind of migration or movements so that we don't lose them from the cathode to the other part of the battery. So yes, so the only crystal structure is the final product is the lithium sulfide, and then when you charge it back, it goes to cycle again, it becomes the ionic species, and then all the way back to here, back to S8. So that's how the cycle goes. So, and then, so yeah, yes, they are basically dissolved in the medium. And, you know, the only solid is the starting material S8 and lithium-2S. Those are the solid. Do I answer your question?
Yes.
So if there are no more questions, we're at time. So we'll stop the recording here. Thank you for joining us for the first ME Research Seminar. Next week, we have Pierre La Rochelle talking about robotics and additive manufacturing. Same link and everything. Right. Same Zoom link, time, channel. Thank you, everyone.
Thank you.